Hey, it's Mr. Saltano. This video is going to be explaining the Bohr model of the atom. So first of all, it was Niels Bohr who came up with the Bohr model, and the way the Bohr model works is that he suggested that electrons orbit around the nucleus at specific distances, which relates to the electron's energy, their energy level. So the further out the electron is from the nucleus, the higher the energy. And without that motion of those electrons, basically they'd be drawn into the positive nucleus, because the nucleus is positive and the electrons are negative. So without having a certain amount of energy, they would be pulled into the center. Another important thing is that we call the first shell n equals 1, so that's the innermost shell of the Bohr model, and the furthest shell out is called n equals 7, so the number goes up the further we go out in shell number. So we start with n equals 1. So just to give you a better idea of what this is like, they call Bohr's model the planetary model because the electrons orbit the nucleus in his model, much like the planets orbit the sun. And so this also makes it easier to think about the energy levels because, like we said, the higher the energy level, the higher the level, the more energy it would take for an electron to be out that high. So electrons further away have more energy. A way to think about this is, imagine you want to launch a satellite and you want it to orbit the Earth, right? The way a lot of our satellites do. If you want that satellite to orbit the Earth from a further distance, you would have to use more thrust to get that satellite out that far, right? And that's how it works with the electrons too. The bigger the atom, the more energy those electrons on the outside have. So how the Bohr model works, the first thing you have to do is it arranges the electrons in specific energy shells, or energy levels. And the other important thing is that the electrons cannot go between those energy shells. So you cannot have an electron at like n equals 1.5 or something. It would have to be either 1 or 2. So if you look over at our diagram over here, here's someone climbing a ladder. You cannot step between the rungs of a ladder, just like the electrons cannot be existing between these energy levels. They have to be at one energy level or the next. There's no in between. In order to tell the maximum number of electrons per shell, you can use the equation 2n squared, where n is the shell number. So we're going to be going through that soon. And the other important thing is you have to fill the lower energy levels before you fill the higher ones. So you have to fill the first shell before you can start filling the next shell. You can't just randomly fill them with electrons. Okay, so here's our 2n squared formula. This is how we know the maximum number of electrons per shell. It doesn't mean it's going to be how many are on that shell per se, but it means the maximum that can fit. So if our first shell is n equals 1, then what's the maximum number of electrons that can fit? Well, what you have to do is you have to first square the 1, so 1 squared, and then you multiply it by 2. A lot of people tend to forget that. Remember PEMDAS, do the exponent and then the multiplication. So if we do that, what would you get for the electrons in the shell if you square the 1 and then multiply it by 2? Well, you would get 2, right? What about for the next energy level? So n equals 2. So if we look at our diagram, this is the next energy shell. For n equals 2, what would you get for that number? Well, you'd get 8, because don't forget you square the 2 first, which gives you 4, and then you multiply it by 2. What about for the next energy level 3? Well, you would get 18, because first you square the 3, and then you multiply that 9 you just got by 2. And that's, again, the maximum number of electrons that can fit in the energy shell. It doesn't mean you're going to have that many, but it's the max that it can hold. So let's start doing helium first. So I'm just going to show you this example. So the atomic number of helium is 2, which means we have 2 protons. But what we're focused on is that we have 2 electrons in a neutral charged atom, right? So the way I'm going to fill this, well, first of all, I know the first shell holds those 2, so I can fit both of them on the first shell. And I'm actually going to stop there. Another important thing, if you notice, is that I kept these electrons as far away as possible from each other. Whenever you fill these shells, these electrons need to stay as far away as possible. Now, why is that? Well, it's because the electrons have similar charge, right? They're both negative, and things that are the same charge repel each other. They want nothing to do with each other in chemistry. If you have two things of the same charge, they want to get away from each other. So, two electrons as far away apart as possible. This is the whole Bohr model for helium. And and something else is very important is that the valence electrons, which are the electrons in the outermost shell, the valence electron count is 2 for this. Now the reason our valence electrons are so important is because those are the ones that partake in reactions. Okay, so let's look at another one. So for lithium, lithium has 3 total electrons. So remember, you can use our formula. Our first energy shell holds 2 according to the formula. So we can go ahead and fill those 2 as far away apart as possible. And then we have one more left and we can start moving on to the next shell because we filled the first shell. And that is the Bohr model for lithium. Now, how many valence electrons does lithium have? Lithium has 1 valence electron because even though there are 3 electrons total, we're worried about the electron that's on the outermost shell because that's the one that's actually going to do the reaction. So if you react lithium with something else, this outermost electron is the one that participates in the reaction. These ones not so much. And that's going to be really important for reactions in chemistry. Okay, what about boron? Well, we know our first shell holds 2. And our next shell holds 1, 2, 3. Now, notice that I spread these out as much as possible. So this looks different than you might see in some of your Bohr models because I tried to put these electrons in that outer shell as far away as possible. And our valence electron count for boron is going to be 3 because we have 3 in the outer shell. Okay, what about neon? So we fill in first 2 shells. First shell of neon can hold 2, right? And then what's the maximum our second shell can hold again? Well, we do 2, n equals 2 is our second shell. We square it, and that gives us 4, and then multiply by 2 gives us 8. So we can fit all the rest of those 8 electrons on that last energy shell. And the valence electron count is 8 because that's how much we filled our outer shell with. Sodium. So we got to do sodium. Remember that we can fit 2 in the first shell. We can fit 8 in the second shell. So that'll bring us all the way up to 10 because our 2 here and our 8 here give us 10. And then that means we have to move on to the next shell. We can fit 1 more in the next shell. So what is our valence electron count then? Our valence electron count is 1. So only one of those electrons, that outer shell electron, is going to be the one that's reacting for sodium. Okay. Now if we quickly create the Bohr models for beryllium and magnesium, we're going to do a comparison here that you might find a little bit interesting. So we're going to do beryllium. And according to the periodic table, beryllium is atomic number 4. So we do 4 for beryllium. So how many valence electrons does beryllium have? Well, it has 2. Then we do magnesium. Magnesium is a number 12. So we fill our first shell with the 2. We then fill our next shell with 8 more, right? Because that's what our rule says. And then we have 2 more left that we can use in the outer shell. Now what do you notice about beryllium and magnesium about their valence electron count? Well, they both have 2 valence electrons, but notice in the periodic table, they're in the same column. So that's directly related actually. The valence electron count has to do with what column you're in. And so we can actually do a whole pattern for this. So the first column in the periodic table all have 1 valence electron. Doesn't mean they have 1 total electron, but they have 1 electron in the outer shell. The second column has 2. And then if we skip over the middle, the next column where boron is has 3. And then we go on 4, 5, 6, 7, and 8. Now, something important to mention is that helium obviously cannot have 8 valence electrons, but the rest of the column does. So helium is the exception to that. But that's really important for valence electron count. The other important thing is, if you notice, is that the rows, the horizontal, is actually the shell number. So n equals 1 is filled in the first shell. The next shell is n equals 2. So if you look at our beryllium, for example, we got to the second shell and filled that. That's where we ended. And then the next shell level is actually the 3rd row down. So magnesium, we had to go to the 3rd shell, n equals 3. So the energy level is the row, and the column is the valence electron count. This is going to be really important going forward. Okay, so now we can actually make a prediction about our Bohr models without even doing all of the counting, for example. So if we go to do carbon, well, carbon is going to have 1, 2, 3, 4 valence electrons, and we know it's going to be in the second row, right? So we do 1, 2, and then we do 1, 2, 3, 4, and that's it for carbon. That's its 6 total electrons. And then we go to do sulfur, and sulfur is in the third row, and it's over here in the 6th column. So it's going to have 6 valence electrons, and it's going to be on the n equals 3 shell. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and that's going to complete sulfur. So we predicted that properly as well. And again, we have our shell n equals 1, n equals 2, and n equals 3. Okay. So what's going to be very important with this is that even though we now have the shortcut, you do want to practice that formula 2n squared, because you need to be able to remember how many electrons fit in each shell according to the Bohr model. So you can use the periodic table to help you. It's great to have these shortcuts and to have an understanding, but you do also want to make sure that you can do it even if you don't have a periodic table with you. You just have the atomic number if you're just given the information about that atom and not where it is, for example. So that does it for us. Thank you for watching, and remember, chemistry is everywhere.